Hello, in this video I want to talk about Cartesian product. And we will implement the function which generates to us the Cartesian product from a given set. Let's call this function C, and let's call Cartes. Let's call it Cartes or CRT. And it takes some list access, and the simplest way to generate Cartesian product is to do it with do notation. So we, for example, we want to generate a pairs. Okay, so we take some x from xs, and we take some y from xs, and we return some pair. Okay, or list, or we can return to list with x, with pair x and y. Let's try to compile this. And try to run this function, and we can see that it works. It generates me all possible pairs on this set. Also we can generate it using applicative and functor type classes. So how can we do this? We have this tuple constructor, and we can map it to some list. Okay, let's call this function cr. Take some list, and we apply this constructor to this list, and we partly apply it to this list, and it produce a list of functions which is applicable to this list again, and this is give to us exactly what we want. Let's try to check this. Yes, it works. But we can rewrite this a little bit. We've left R2 function, which will lift this tuple constructor to our xs list. Let's just redefine this. xs reload. No modules. This function in control applicative module. Yes, it works. So for example, if we want not tuples but lists, we can rewrite it a little bit. We can use lambda here, which takes x and y and produce list x and y. Okay, this also should work. Let's check. Sorry, I don't need this here. Lambda, fuck. Python legacy. Okay, let's check this here, and it also work, but it gives to us a list. So but what if we want to produce triples, not only tuples, but triples? Of course we can do it, we can rewrite this with a free function, lift a free function, which produce lists with three elements. Let's redefine and check. Yes, it works. And so on. We can produce elements with 4, 5 and more elements using lift 4, lift 5, etc. So the arity must be the same, and we need to rewrite this lambda. Also, there is a very interesting function which called sequence, and it can be used to produce Cartesian product. Let's see how it works. Sequence, and we must to give to it a list of lists. For example, 1, 2, and 3, 4. Okay, and you can see that we have Cartesian product, and we can add more lists here. And it will give us exactly what we want. So if we get 2 free lists, we get triples, and so on. But what if we want function which takes the number of elements as parameter and produce the list with this number of elements? We can implement this function. Let's name it CRN, and it takes list and number. How many elements in the begin rate, how many elements in one item. So how we can define this? First of all, it takes initial list XS, and via bin to we bind every element to X in Closely arrow, and we need to produce a monad here. To produce a monad, we will use again our CRN function and put XS as first argument, and in second argument we will reduce our task to lower level. And because we do this reduce, we need to every element of this subtask get via functor our chosen element X. And this will give to us what we want. Let's check that this works. CLN 1, 2, 3, 1. It can be because I didn't define the lowest case when they take no matter what, and the n is 0. We need to return an empty list. The list we want empty list. So reload and run this 2. You can see that this is a correct result. Okay, run the 3, and this is a correct result. Of course, we can expand our list and take our results. So I think that's all what I want to say about Cartesian product, and thank you for watching. Push like button, push subscribe, and write comments. Bye.